Okay, podcast APChem practice exam for chapters 1 through 3. Today is 8/31/07, so hopefully that helps you. There are a number of parts. The first part is multiple choice. And so question number 1, let's talk ourselves. How many cubic centimeters are equal to 1 cubic meter? So a cubic meter is a meter cubed. So 1 cubic meter equals how many cubic centimeters, right? Well, of course, you know there's 100 centimeters is equal to 1 meter. So what you would, of course, need to do, if you're going to cube it, you need to cube both of these. And 100 cubed is A. Okay, not too bad. All right, number 2. If Thomson, the model of the atom, had been correct, Rutherford observed, all right, let me start at the bottom. Now, D. Positive particles formed on the foil. No, remember in the Thomson model of the atom had been correct. When he shot the alpha, remember Thomson model had like little, he called them corpuscles, or basically shot electrons. If he had done this, what would happen is the alpha particles, these are the alpha particles, as they travel through, they would go through the foil with no deflection, little or no deflection. So this is what he expected, letter A. Number 3, and that's not what happened, of course. Which compound has the highest percent carbon by mass? Well, what you can do is you can actually figure each of them out. You'll take the, remember this is a percent composition, okay, and you would take, for letter A, you would say 24 plus 4 plus 16 be 28, 38, 42, whatever this comes out to be, and you'd say 24 over that. 12 times 2, carbon weighs 12, and that comes out to 0.54%. And you basically do the same thing for the carbon dioxide. For the carbon dioxide, you get 0.27%. For the CH3Cl, you get 23%. This is not 0.27, 27%. For the C2H6, you get 80%. So, of course, that's the answer, C2H6, letter D. Kind of paged weird, but that's okay. Number 4, many classic experiments have been given as indirect evidence of the nature of the atom. Which of the experiments listed below did not give the results described? Letter A, the Rutherford experiment proved the Thomson plum pudding model of the atom to be correct. Well, it turns out Thomson, of course, was not correct, so we don't have to go any farther. A is the answer. And the others are good. When the following equation is balanced, what's the total sum of the coefficients? Now, what you want to do oftentimes is put a 1 right here and try and figure that out. And you've got Al2, CO3, 3. And so then what I would do is I would look at let's look at the carbons. So there'd be 3 carbons here. And then I want to look at the, say, oxygen's in 2 places, so I'll wait on the oxygen. Let's now do the aluminum. So there's 2 aluminums. So if I put a 2 here, now that gives me over here 6 chlorines. So I would need a 6 here, which would make this right here a 3. So, important, one thing to watch here is you do have a 1 there. So it's 1 plus 6 plus 2 plus 3 plus 3. And that, of course, adds up to 15. Number 6. Consider the element iridium, atomic number 49. So indium is In, and this is 49, and his mass number is 115, essentially. We'll round that up. So he's going to have 49 protons, and he's going to have 115 minus 49 neutrons, which turns out to be 63 neutrons. He's also going to have 49 electrons. So if you look at A, that looks like the correct answer, and then you've got D. So what do you do with that? Here, very important, it says the nucleus of the atom, so that's why D is the correct answer. Watch that. That would be a tricky one, wouldn't it? All right. And number 7, the chemical oxidation of aluminum occurs at the reaction, so aluminum plus oxygen, and it turns into Al. Now it says aluminum 3, it would be Al2O3. Now this is a tricky one to balance because you've got a problem here with your oxygens. So to do your oxygens, you need to put a 2 here and a 3 here, which makes this a 4. Now it says you were given 32 grams of oxygen and 27 grams of aluminum. Now if you do real quick here, the atomic mass of aluminum is 27, the molar mass of molecule of oxygen is 32, so you essentially have 1 mole of each. Okay, so which one then is limiting? So then you're going to convert 2 grams of aluminum. Now, you could do both, but frankly, the idea is the one you need more of. Since you have 1 mole and 1 mole, you need more aluminum. So I'd say 1 mole of Al over 1, and then I would say 2 moles of Al2O3 to 4 moles of Al, and then you'll say grams of Al2O3 to 1 mole of Al2O3. And the atomic mass of aluminum oxide is 102, and this comes out to be 51 grams. So 51 grams, letter B, is the correct answer. Not horribly difficult. All right, in 8. There it comes. Which of the following statements is or are true? Okay, oxygen 10 and oxygen 19 have the same number of neutrons. All right, so this is going to have 19 minus, and if I look up fluorine on the periodic table, 9, that's equal to 10 neutrons. And oxygen 10 will be 10 minus 8, which is 2 neutrons, so A is not correct. Carbon 14 and nitrogen 14 are isotopes of each other. That's not correct, because to be an isotope of each other, it would have to be the same element. Oxygen 18, 2 minus, has the same number of electrons as neon. All right, so electrons, remember, oxygen has 8 protons, and he normally has 8 electrons if he is a pure element. But when he has a charge of 2 minus, he'll have 10 electrons. So that's the O2 minus. And then the neon has 10 protons and 10 electrons. So they do have the same number of electrons. So C is the correct answer. Number 9, a sample of metal has a mass of 3.87 grams and placed in a grad cylinder containing 50 mils of water. And then we get a displacement. What's the density of the metal? The correct number of significant digits. So the density, of course, is mass over volume. So now the volume went from 50.0 and it was 55.5, so it went up. So I subtract, that's 5.5 milliliters. It's important to note we now have gone to 3 significant digits. So it's going to be 3.87 grams divided by 5.5 milliliters. This needs to be round to 2 significant digits, so the answer is 0.70 grams per milliliter. If you have more significant digits, you are incorrect. The boiling point of a particular substance is 85.4. Converted to Kelvin, it will be 85.4 degrees Celsius plus 273. Actually, technically, it's 0.1, by the way. I'm not sure you knew this. And then it comes out to 258.4. Or 300, pardon me, and 58.4. All right, now we move on to testing 1, 2. Sorry, that was loud. I thought I heard a weird thing on my mouthpiece. Nomenclature. All right, what is the name of these different things? Iron 2 cyanide. Thiocyanate would be FeSCN2. This is BaHSO3-2. This would be CaMnO4-2. This would be a tricky one. Hg2I2. Remember, mercury 1 is Hg2 positive, and iodide is -1, and so you'll need 2 of these, so that's the tricky one, isn't it? Sodium selenate. Now, selenate's a weird one. Selenate is SeO4, so this is Na2SeO4. This is the selenate ion, which is SeO4 2-. Letter F, nitrous acid is HNO2. Cesium phosphide will be CS3P. Hydroiodic, HI. Rubidium oxide will be Rb2O. And manganese hydroxide, manganese 2, will be MnOH2. All right? And I'm just going through the answers. If you have questions, I'm not going to work them out too much. This has got 2 nonmetals, letter A. So this is going to be dichlorine heptoxide. All right? This is ammonium. It's ionic. Bicarbonate. You could also say hydrogen carbonate. This is an acid, and ends in 8, so this is chloric, CHLOR, chloric acid. KO2. Oh yeah, that's a weird one. That's potassium superoxide. Let's not worry about that one. That's really not that important. This is sodium cyanide. We didn't really talk about superoxides. All right, this one would be sodium acetate. Don't need a Roman numeral because sodium is not. This will be lead. Now, figure out the charge. She'll be lead 4 nitrate, because nitrogen or nitrate, has, of course, has a -1 charge. This will be nickel 2, Roman numeral 2. That's 4 there. Chloride. HBRO. BRO, of course, is bromite. So hypobromite. So this is hypobromous acid, and this will be potassium dichromate. All right. Now it's problems. All right, hold on. Let me jump down to the first problem so some space to work at. We kind of did one of these in class. Gallons, average atomic mass of 69.2. We have two different masses. What are the percent abundances? So we're going to say 68.95. Okay, times something is equal to something. And then we got 70.95 times something is equal to something. But they both add up to 69.723. So now what you do is you say, let's call this x. So this will be 68.95x. And this will be 1 minus x. And this will be 70.95 times 1 minus x. Now we simply need to solve for x. So you get 68.95x plus 70.95 minus 70.95x is equal to 69.723. You subtract appropriate sides, and you get negative 2.00x is equal to negative 1.227. You solve for x. X is 0.6135. So the gallium-68 has a percent abundance of 61.35%. The gallium-71 would be the difference, 100 minus that, so that's 38.65%. Again, you may want to pause some of these because they're at I'm going fast. So let's look at question number 2. The characteristic of the pineapple odor is due to ethylene butyrate, etc., etc. Here's the whole problem right here. And so what is the, all right, I lost the question here. Hold on. Let me pause. So this one, I think I'm going to go on a separate sheet. I think a blank piece. All right, you've got a CHO compound. It's CHO. That's ethylene butyrate. And you're going to react with oxygen, and it's going to make CO2 and H2O. Now, what do you know about this right here? You know that combustion of this is of 2.78 grams. All right, 2.78 grams of this yields 6.32 grams of carbon dioxide and 2.58 grams of water. So to do the carbon, you're going to take 6.32 grams of CO2 over 1 times 44 grams of CO2 and 12 grams of carbon, and you get 1.72 grams of carbon. For the hydrogen, we're going to say you have 2.58 grams of water times 18 grams of water for every 2 grams of hydrogen, and you get 0.2867 grams. Now to get the oxygen, you will take 2.78 grams, that's from up here, minus the sum of 1.72 grams and 0.2867, and that comes out to be 0.7693. Doing this fast, I know this. Now to convert 2 moles, you divide by 12 here, divide by 1, divide by 16. This comes out to be 0.1437 moles. This, of course, is 0.2867, and this comes out to be 0.048. Now you divide by small, so I'm going to divide by small. The smallest number is the 0.048. And so you get, for this one, you get 3. For this one, you get 6. And, of course, you get 1 here. So it is going to be C3H6O. So if it's C3H6O, getting a new screen here, I cannot C3H6O, his molecular, this is the empirical formula. We know the molecular weight is 58. No, is, pardon me. Yeah, it's 50, basically. It's between 100 and 150. The empirical weight of this, when you add this up, you get 58. This adds up right here. 12 times 3 plus 6 plus 16. That adds up to 58. So you need to times this by 2. And so the real formula is C6H12O, well, not 6, O2. Okay? So that's question number 2. What about number 3? The molecular formula of hydrocarbon can be determined by atomic combustion. The molecular weight is 56. All right, so the hydrocarbon burns completely. Now, this is a hydrocarbon. Oh, don't tell me. Test 1, 2, test. All right, hold on. Lost my pen. All right, we have issues. Oh, there it is. All right, sorry. All right, this is a hydrocarbon. That means it's just a Ch compound. Okay, so it's going to be CH plus O2 makes CO2 and H2O. And we know we have hydrocarbon burns produces 7.2 grams of water, 7.2 grams. Oh, and 7.2 liters. Oh, hold on, I got that one. This is 7.2 grams, and this is 7.2 liters of CO2 at standard conditions. What is the empirical formula of the hydrocarbon? So this one's a little bit here, isn't it? Because we've got an issue here. Actually, I'm going to recopy that. So I'm going to say 7.2 grams of water. This will be the easy one. We've done this step before. Then you're going to say 18 grams of water for every 2 grams of hydrogen. So that we've done this before. This is 0.800 grams of hydrogen. And then for the liter one, I'll take 7.2 liters of CO2. And you might remember that there are 22.4 liters of CO2 in every 1 mole of CO2. And then you can convert that to grams. There's 44 grams of CO2 for every 1 mole of CO2. And then now what we can do is we can say 44 grams of CO2 in 12 grams of carbon. So this is a little longer process, and you get 3.857 grams of carbon. So then you're going to take, and let's now present the mass. We've got the masses. Let's do H and C. The H is 0.800 grams over 1, and there's 1 gram in 1 mole. So this is 0.8 moles. The carbon, we have 3.857 grams of carbon, 12 grams of carbon in 1 mole of carbon. And you get 0.3214. Divide by small, 0.3214, 0.3214. You get 2.5 and 1. So what do now? You times both by 2, so you'll get 5 here and 2. So it'll be C2H5. Now that answers question I. Question II. All right. You have a blank screen here. So question II. You have C2H5. So it says calculate the mass in grams of O2 required to complete the combustion. You have to write the balanced equation. So plus O2 makes CO2 plus H2O. We can now officially balance the equation because we now know the we know the formulas. So you're going to do a 2 here, and actually we're going to have to double this. So this will be a 4, and then you've got 10, so that makes this a 5, and we have 8 and 5 is 13, so that's 13 halves. Oops, 13 over 2. I'm not sure if you need that actually. All right, so calculate the mass in grams of O2 complete combustion of the sample described in Part A. So I know that I had whatever it was, 7.2 grams of this. and I need to convert to the O2. Now, by the way, some of you are going, wait a second, how could he have a half? It's okay to have a half. You can do that. It's not a big deal. So I'm going to take 7.2 grams of H2O, and I can say 18 grams of H2O to 1 mole of H2O. And I'm going to say 13.5 is 6.5 moles of O2 to 5 moles of water, and then 32 grams of water, or of O2, for every 1 mole of O2. And this comes out to be 16.6 grams of O2. All right, and then we have the third part of this, I, and it says that what is the molecular formula of the compound? We know that the atomic molar mass is 56 grams per mole, and we know that it's C2H5. When you add that up, that comes out to 29, so this is a times 2, so it'll be C4H10. By the way, that previous problem, if we would have I used an empirical formula, it'll still work. Where did it go? It would have been a better thing to do part C first, and so if you'd have written C4H10, it would have been easier to balance. So, but you'd still get the same answer because the ratios and the proportions are though. Okay? Question 4. In the following equation, we need to balance it. So how do I balance this equation? I've got a nitrogen here and a nitrogen here. So I'm pretty pleased with the nitrogens. This is a tricky one to balance because how are you going to think through this balancing one? The oxygens are all messed up. You got to kind of keep playing with it. You got 2 hydrogens here and 3 hydrogens here. So at the worst, I'm going to need to double this. Put a 2 here, and that would make this a 3, right? And that gives me 2 nitrogens, so I'd have to put a 2 here. And then what does it do to my O's? I've got, on this side, I got 4 O's here, plus 3. I got 7 oxygens, and on this side, I can't make it work. So I'm going to need to double it. So if I've got, I'll write it down here, NH3 plus O2 makes water plus NO2. NO2, by the way, is that brown gas that you did in the lab today. So you're going to double this. If this becomes a 4, then there's 12 hydrogens, then this number here is going to have to be a 6. And that makes this a 4. And when you do the math, that has to be a 7. A little tricky on the balance on that. All right, what is the limiting reactant? Use values from part 3. So we have to look at part 3. So we've got a problem here, all right. So let me re-equation. I've got 4 NH3s plus 7 oxygens makes 6 waters and 4 NO2s. Now what do I know? I know that I've got 22 liters of ammonia with 95 liters of air. Now that's air. So we got to actually do a little mathematics. Only 20% of air is oxygen, so 95 liters times 0.20 is equal to, all right, let me pause it and get the, it's equal to 19 liters. So this actually here is 19 liters of oxygen, all right? And now what we're trying to do is find out what is the limiting reactant. And so what you want to do is, actually, let's try and figure out, yeah. Now there's this shortcut that I would like to tell you about. If you've got 22 liters here and 19 here, and this requires 4 parts and this requires 7 parts, remember there's the old Cherry Creek method. I'm not sure I called it the Cherry Creek method, but if you divide by the coefficient, then you will get the lowest answer wins. So 22 divided by 4, this number drops down to 5.5. And if I take 19 divided by 7, this is 2.7. The answer is the oxygen is limiting, because that's the one that's lowest. Now the question is how much excess reagent remains. You would convert the limiting reactant, the oxygen, to the excess reactant and subtract. So you'll take 19 liters of O2 over 1, then you'll say 22.4 liters of oxygen to 1 mole of oxygen. Actually, it's a bit redundant, and I'll explain that. Then you'll say 4 moles of ammonia to 7 moles of oxygen, and then you'll do the 22.4 liters of ammonia to 1 mole of ammonia. And you get 10.8 liters of ammonia. So then what you do is you started with 22, so 22 minus that gives you 11.2 liters left over. All right? I believe we've got question number 5. Hold on, let's see. Oh, here it goes. In the following reaction, and here it is, 12.6 grams of sodium nitrate is produced with the addition, what is the percentage of yield? I need a blank screen because I need space, you know me. So let me rewrite the equation here. So bear with me. PbNO32 plus sodium sulfate, Na2SO4, makes the precipitate lead sulfate, PbSO4, plus 2NaNO3. If I have 12.6 grams of sodium nitrate is produced, and I started with 25.3 grams of this, what's the percent yield? So you're going to convert from here to here and then do a little division. 25.3 grams of sodium nitrate over 1. Molar mass of sodium nitrate, add it all up, comes out to be 142 grams of sodium nitrate, 1 mole sodium nitrate. All right, and then I'm going to convert here. The ratio here is 2 to 1, so 2 moles. Actually, this is sodium sulfate. Sorry about that. Na2SO4. And then we'll have 2 moles of sodium nitrate to 1 mole sodium sulfate. And then we multiply by the molar mass of sodium nitrate, and you get 85 grams of sodium nitrate to 1 mole of sodium nitrate. That comes out to be 30.3 grams of sodium nitrate. So this is how much you expect to get out. But you actually only got out 12.6. So what is your percentage? Well, you'll take 12.6, divide by 30.3 times 100, and you get 41.6% yield. Okay, hope you prepare for the test. Study hard.